Hello everyone. In this video, we are going to learn how to model a traffic signal structure using the SAFI HSE application. The SAFI HSE software is a leading structural engineering software for the generation, analysis, and design of various sign structures. The software accounts for the advanced structural analysis and design of steel and aluminum latticed highway sign structures, overhead sign structures, gantry structures, cantilevers, traffic signals, and luminaire support structures according to the latest American and Canadian standards such as CSA S6-06, CSA S6-14, AASHTO LTS-13 ASD for steel, and AASHTO LTS-15 LRFD for steel and aluminum. We are going to present in this video a full example of a highway sign structure. This will include how to generate the structure with all of its details. We will also assign all the required loads, the design parameters, and run the analysis and design. At the end of this model, we'll be looking at the analysis and design results for the structure analyzed with the AASHTO LTS code. Let's begin this model by adjusting the units. So, we'll go and set the units to imperial units. Now, let's say the lengths are defined in feet. Before we start generating the model, we'll make sure every section is already defined. Let's take a look here. Before we started this presentation, we created a few sections that we'll be using for this model. This will be faster and more efficient. Here are a few different sections that were created. Each of these sections are associated to a specific material. If the material you want is not on the list, you can go ahead and use one from these lists or create a new material here. There is also another command for non-standard sections. In this case, we've created a dummy section using a generic material. This section will be used for member offsets. Then, let's create the geometry. Here, we are inside the highway sign wizard. Either you can select the Canadian code, or the AASHTO LTS code, LRFD, or ASD. We will go ahead and select the LRFD in this case. You also have the option to create this type of structure. If the structure is not in the list, then you can select the manual option. Let's select this type of structure. You may have up to 3 vertical supports. So, let's go to the next step. Now we'll have to specify the dimensions of the beam. The length is 45.5 feet. The beam extensions are equal to 0.52 feet on both ends. Let's say we have 11 divisions inside this panel. We'll create another panel with the same properties. Here, we can specify the size dx and dy of the beam. Then, we are ready to go to the next step. Here, we can define the height of the support to 29 feet. T1 and T2 can be used in case you have a tapered column section. In this example, since there is no variable section along the columns, we can leave these two inputs to 0. The dimension B is equal to 1 foot and SV is equal to 5.748 feet. And the cantilever at the end of the beam is equal to 0.5 feet. There is no internal sleeve tubing at the column base. Then, we'll input the same values for the other support, although they could be different. Let's go ahead to the next step. Then, let's assign a section to the beam members. we'll select section 1 for the main beam. And then, for the diagonals, we'll select section number 2. The offset distance at the end of the diagonals is left to 0. And then, the same input for segment number 2. For the column, let's select that type of structure lacing. We'll just verify if we use the correct option for the beam too. Let's go back to the column. The main column section is section number 3. It's the same at the bottom and at the top. And then you have section number 5 for the beam support here, and the diagonals with section number 4. And then, for the other support, we'll repeat the same input. You could also add a pedestal. Let's just show you what it would look like. Here is one of the many pedestals that could be added at the bottom of the main support. For this structure, there are no pedestals. We'll just erase this one for now. Then, we'll go to the next step. For the fatigue verification, we'll just click the default button to get the input filled quickly. Each of these inputs that represent the maximum allowable threshold for different connections inside the structure can be modified. If you're not sure of the meaning of these inputs, you can click on the Help button where more detail can be visualized for each input. For example, the stress in the support cord at a diagonal attachment, delta sigma 2, would be this value, and the stress in the diagonal attachment to a support cord, delta sigma 1, corresponds to the end connection. We could put a different elevation at the base so the wind profile would be increased automatically for cases where the structure is above the ground. For this case, we'll leave it to 0. Now, the model is generated. We could have a more representative overview of the generated model by looking at the solid modeling view. Let's assign the anchorage rods. The anchorage rods can have two different types of layout. The software does not specifically design this particular connection type or the base plate thickness. This command is used to design the anchorage rods. Let's specify the bolt circle diameter based on the column tube diameter. The dimension H is left to 0. Let's select the anchorage rod material strengths. Based on the specific connection detail, you can figure out what is the maximum fatigue threshold stress. The actual units are in pounds per square inches. And then, let's also select the concrete strength. Now, we'll select this point as the reference point, and then we can specify the panel dimensions. There are different types of panels you can use. We'll show them in another video. So, let's say we are just selecting a simple panel here. The size of the offset panel is 17 feet according to the reference point, minus 4 feet for the vertical offset. The dimensions are 20 feet per 12 feet. And the thickness of the panel used for the truck-induced gust load is set to 0.125 inches. The self-weight is equal to 7 pounds per square foot. This panel is now displayed on the screen. So, we'll create another one similar to that one just beside it. As both panels are similar, we'll just click here to create a copy of the existing panel. The first one could be called P1, and we'll create another one called P2, and we'll have an offset from the reference point of 53 feet for this panel. Now, we also have to assign the wind and ice loads to the structure. The self-weight is already applied as shown on the screen. Let's apply the additional loads. From this map button, we can select the appropriate location. The state is Alabama and the county is Mobile. Let's say we have a wind recurrence of 1700 years. These inputs can be modified as required. For example, you can change the wind speed without ice. For example, you can change the wind speed without ice. There is also the wind velocity associated to an ice thickness. Let's say the ice thickness is equal to 0.25 inches. The wind velocity for this case can be found in the AASHTE 10-7 map. You can look at the help option for more information. In this image, we can see that figure 10.2 from the AASHTE 7-10 code, which shows the wind velocity for the wind on ice case. Let's say in this location the wind on ice velocity is equal to 35 miles per hour. We can specify the importance factor for fatigue. And let's say we enable the natural wind gusts for the fatigue. For the truck-induced gusts, if you specify the width of the lanes, the generated design loads will be more precise. We are now ready to run the analysis. So, let's save the model and adjust the structure view. One last thing before we run the analysis. We'll just have a quick look at the generated loads. From here, we can have a look at the loads. Let's look at each of them separately. Here's the dead load. Here's the wind applied along the z-axis. Notice that the axes are displayed here. We also have the wind along X and also the ice load. There is also the wind for service verifications and wind on ice. There is also the wind cases for the natural wind gusts for fatigue. Also, there is this vertical pressure due to the truck-induced wind gusts applied to the structure at different locations. So, we'll get the worst case. Let's hide the loads temporarily. The software also generated the load combinations automatically. So, we can have a look at them here. Here, we have an overview of the generated combinations. All combinations required by the AASHTO LTS code are listed here. This includes all the wind load cases according to all the wind directions. Some are with an amplified dead load, others with a reduced dead load for uplift. There's also cases for the wind at 45 degrees, with the 0.75 load factor for wind on both directions. There's also service cases for deflections and vibrations. And there's also cases for fatigue. The stresses due to fatigue will be verified only for fatigue combination type. We are now ready to run the analysis. Just to confirm the design will be running the correct code, we can have a look at the command that shows the design code. So, we did select the AASHTO LTS-15 LRFD. We also get other design parameters here. So, we are now ready to run the analysis. Different types of analysis can be run as linear or p-delta. Let's say we select P delta to get more accurate results. For the design, we select Steel Verification. We are now ready to click on the Run button. Now, all the analysis and design results should be available. Let's first look at the structure displacement. Here we can see the internal deformation. So, this is the structure deformation due to the factored self-weight. We can also display another combination. Let's select combination number 2. Now, we see the deformation due to this combination. We can also display the applied loads that causes this deformation. We now see that this combination includes the self-weight and the wind load applied in the Z direction. The displayed information scale can be changed to something more realistic. We can open the display options and adjust the scale of the displacement. Now, the displacements are still amplified, but with a more realistic scale. We could use the Animate button to have a better view of the structure movement. You can also have a look at the bending and axial forces in the members. We can see the tension and compression forces on the legs. Now, we'll take a look at the bending moments around the strong axes of the members. Here we can see the larger bending moments in the continuous main leg members. You can also look at the limit state design for that structure. To do so, you just have to check the option in the steel section here. The limit state legend is displayed. The displayed colors on the structure correspond to the current combination. Let's say we select all combinations. Now, the displayed colors are for the worst case. We are now looking at the worst limit state. The software performs verifications for many limit states. They can be displayed separately. For example, we can look at the compression limit state. Then, the tension limit states. We can also have a look at the fatigue. Notice that for this structure, the fatigue limit state is critical at some locations. Also, note that for this structure, all limit states remain below 1, which means the design is safe. You can also display the results per table. So, let's say we would like to get the limit states for this member here. We can select the member to get only its results. Let's see the numerical results. We could look at the limit state summary, so we can easily see for which combinations the limit states are at the maximum. Now, we see that the controlling criteria is the fatigue limit state with a value of 90%, and that the other limit states are lower for that combination and also for other combinations. Now, for example, for this member, we could look at the fatigue limit state more closely. Again, we can view that the fatigue limit state for this member is around 90% here. Also, that the 0.9 ratio comes from the actual stress range divided by the allowable stress range. Now, the threshold stress range is equal to 1200 psi, and the actual stress range is 1081 psi. If you are not sure what these columns mean, you just have to click on the Help button and read the associated information. One last thing we could have a look at in this example is the reactions at the foundation to get the design of the anchorage rods. These 6 columns show the cumulative reaction forces and bending moments at the joint for each of the combinations. The critical anchor rod forces and resistance are also displayed as well as their limit states. From the help, we can see the bolt ID according to the global axes. So, back in the table, you know which rods are the critical ones in this connection. This concludes our video for the steel highway sign structure using the AASHTO LTS-13 code. Thank you for watching. Don't forget to subscribe to SAFI's YouTube channel and visit our website www.safi.com to stay updated on the latest features of the software.